Hi there, Dr. P here, and in this lecture video we're going to take a look at the why behind 1,2 and 1,4 conjugate addition. And so I'd like to start off with a couple of definitions here. And these are actually definitions for the title of the lecture, Kinetic and Thermodynamic Reaction Control. So, thermodynamic reaction control is at high temperature, more molecules have enough energy to overcome a higher activation energy and form a more stable, lower energy product. So at high temperature, more molecules have enough energy to overcome higher EA and form more stable or lower energy product. The other type of reaction control is called kinetic reaction control. And this occurs at low temperature when we have fewer molecules that have enough energy to overcome activation energy. So fewer molecules have enough energy to overcome higher EA. So our lower activation energy pathway is going to be favored. Even if the product is less stable. So that is higher energy. Oops. So remember last time we saw that, so I'll just say here from last lecture, we got the 1,4 product at low temperature. I forget what the exact percentage was. Let me just check the notes real quick. So at low temperature, we got 80% 1,2 product and only 20% 1,4 product. But at high temperature, we got 85% 1,4 product and 15% 1,2. So this guy was favored at high temperature. All right. So I think one of the best ways to really explain this or describe it is to go ahead and look at a reaction progress diagram. So let me draw one here. And so this is for the addition, conjugate addition of HBr to 1,3-butadiene. So I've got energy on that axis, and then I've got the progress of the reaction on that axis, which I just realized you can't see because it's off the, there we go. Keep everything in frame there. All right, so we'll go ahead and start with our, we'll have some, whatever the energy is of our starting material. And then we will have some activation energy associated with the protonation. And so that will now lead us to having our positive charge delocalized. Remember, it's actually spread out over, and I realize I just messed that guy up there. Sorry about that. It should be like this. Because I'm protonating here, grab my proton, it goes there. Positive charge is there, but is also delocalized on carbon 4. So it should look like that. Sorry about that. And then I'll go ahead and I'll have two possibilities. So we'll have our, and maybe I'll go ahead and do these in a couple different colors. So we'll have one possibility in blue here, which is, we'll have a certain activation energy. So this will be EA12, and then we'll get our 1,2 product. But now in red, I'll have higher, oops, there we go, higher activation energy. Let me try to get this leading to a lower energy there. So this is my EA14, and that gives me my 1,4 addition product. So we see here in blue, this is what's going to happen at low temperature. We have fewer molecules of the intermediate that have enough temperature to get over the big hump. So the small hump energy barrier is easier to get over, so that's what's going to happen. But at a higher temperature, we have more molecules that can get over the big hump. In fact, high enough temperature, when we make this product, it can actually do the reverse reaction and go back and forth and back and forth, and with enough energy, a molecule of the carbocation will react with Br- and give us our product, and then it gets stuck here because this really is way too much energy for the reverse reaction to occur. So the idea is that, I mean, really, we have less stable but easier to form. And then on the other hand here, we have more stable and I'll just say harder to form. Technically, we would say that, you know, easier to form is lower activation energy. Harder to form is higher activation energy. And so why is this guy more stable? Well, we've got a di-substituted alkene here. And in the 1,2 addition product, we have a monosubstituted alkene. So if you think back to chapter 7 and the alkene stabilities, the more substituents an alkene has, the more stable. So tetrasubstituted was the most stable, then tri-substituted, then di-substituted, and trans was more stable than cis, remember that, and then monosubstituted. So this is really the explanation for why we get these two different products. And one thing I do want to call your attention to is really these definitions and thinking about what's going on. Because these are the definitions, all right? At high temperature, you get the more stable product. At low temperature, you get the product that is easier to form, lower activation energy. So for your kinetic reaction control, this is going to be the 1,2 product. Why is that? Well, it's actually a proximity effect. If we take a look at the mechanism, so let me grab the mechanism notes from last time. We've got the mechanism here. When our alkene gets protonated, our Br minus is still in the neighborhood, so it could add right away. That's why there's a lower activation energy. Now, if it is going to add to the carbon at the other end, carbon 4, it has to actually move down there. So the delocalization, once we get the protonation, happens instantly. Okay, this is, remember, resonance structures are a man-made invention, and really we've got positive charge delocalized on carbon 2 and carbon 4, and so, you know, spread out like that, but on carbon 2 and 4. Let me get something I can point with here. There we go, 2 and 4. And so, you know, we just added an H here. Our Br minus is going to be close there, so lower energy to do the 1,2. Br minus has to travel along, diffuse along, and add to carbon 4 to get the 1,4 product, which is right there. So the kinetic product is going to be the 1,2 product. I really can't think of examples where it wouldn't be the 1,2 product. There are some examples for the thermodynamic product where and I'm going to say usually it's the 1,4 product, but there can be examples where it's not the 1,4 product. And that's something that I think we'll spend some time talking about in lecture when we meet in person. So again, we have our definitions of thermodynamic reaction control and kinetic reaction control. We would call the product under the high temperature conditions the thermodynamic product, the product under low temperature conditions the kinetic product. And we can see, looking at a reaction progress diagram, really what's going on. The reaction pathway for both products is the same up through the intermediate. And then it's easier to add the bromine at carbon 2. That's our lower energy pathway, but it gives a higher energy product. Then adding the bromine at carbon 4 has a higher activation energy pathway, but gives us a more stable product. Okay, so just some things to note here. The kinetic product is the one that's easier to form, and the thermodynamic product is the more stable one. All right, it's possible that your kinetic and thermodynamic product will be the same. And again, we'll look at some examples of that in class. All right, well, until next time, stay safe out there. Bye now.